Now let's start to bring all of this formalism to bear on the specific problem that we are interested in, the propagation of gravitationally interacting n-body systems. The Hamiltonian of a two-body system can be written as the conjugate momentum of the first body dotted with itself divided by twice the mass of that first body, plus the momentum of the second body dotted with itself divided by twice the mass of the second body, minus the gravitational constant times m1, m2, divided by the difference in the positions of the two bodies, the coordinate sets of those two bodies, which you should 100% verify for yourself that you agree that this gives you something that looks like the total energy of a two-body system. The kinetic energy of the two-body system is similarly the mass of the first body divided by 2 times the time derivatives of the position of the first body, so the velocities of the first body squared, plus the same thing for the second body. So in this case, these q coordinates represent the positions of each of the bodies with respect to some arbitrary point in space. We're going to introduce a change in coordinates such that our first generalized coordinate, or our first set of generalized coordinates representing the vector q1 capital, is the position of the center of mass of the system. And the second generalized coordinate will be the relative position of body 2 with respect to body 1, the thing that we've been calling the orbital radius. The transformed conjugate momenta have to be the partial of the Lagrangian with respect to the time derivatives of these new generalized coordinates. And in this case, the only part of the Lagrangian that will have a dependence on the time derivatives of coordinates is the kinetic energy part. And so this is the same as the partial in kinetic energy with respect to these new coordinates. And so after doing some algebraic crunching, which you should verify for yourself, we find that the first conjugate momenta associated with the position of the center of mass of the system is equal to the sum of the masses times the time derivative of the position of the center of mass, which is exactly equivalent to the sum of the original conjugate momenta. And the second conjugate momenta of the transformed system is equal to the reduced mass times q dot 2 capital, which is equal to m1 times p2 minus m2 times p1 over m1 plus m2. If we rewrite the Hamiltonian of the two-body system in terms of these new coordinates, we will find that we have one term that is the Hamiltonian of the center of mass, p dot 1 dotted into itself, divided by twice the total mass of the system, plus something that describes the Hamiltonian of the Keplerian system, the two-body orbit as described by the relative orbital radius between the two bodies. And that looks like capital P2 dotted into itself over twice the product of the masses times the sum of the masses minus gm1 m2 over the norm of capital Q2. The key point to be taken away from all of this is that the two-body Hamiltonian is cyclic in the capital Q1 coordinates. The center of mass coordinates are ignorable, and P1 is a constant of motion, which we knew all along. We started out with this basic result that the center of mass of the two-body system does not accelerate and does not in any way contribute to the dynamics of the system. It is completely ignorable. We can just focus on this H Kepler part, the Keplerian interaction of a two-body system, and ignore whatever the center of mass is doing because it does not affect our dynamics whatsoever. We are now going to repeat this procedure for the n-body case. And we will introduce what are known as Jacobi coordinates. The n-body Hamiltonian, generalized from the previous slide, is the summation of all of the individual bodies' momenta, scaled by twice their masses, minus all of the mutual gravitational interactions given by this double summation. We have introduced a slightly modified indexing scheme here to correspond to the historical literature, and in particular a paper by Wisdom and Holman, 1991, and all of the works based on that have come since then. So in this case, we are numbering the elements of our n-body system from index 0 to index n minus 1. And typically we will put the dominant or most massive body as the index 0 body. So if we are, for example, integrating the solar system, the sun gets index 0. Our goal is to, just as we did in the previous slide, split up this Hamiltonian. But in this case, we're not just going to have a Hamiltonian of the center of mass, which we can ignore, and a Hamiltonian of the Keplerian interaction, the two-body interaction. We're going to have the Keplerian Hamiltonian which we know that we can solve exactly, plus the interaction Hamiltonian between each of the pairs of bodies, all affecting one another gravitationally. And that is the bit that we have issues with. That's the bit that does not allow for an analytical solution for the m-body case. As before, we are going to introduce modified coordinates. We will call them r sub I prime, and they are defined such that the first coordinate, the index 0 coordinate, is the total center of mass of the whole system. And we will introduce a more compact notation such that we can call this c sub n minus 1, where in general, c sub j is defined as 1 over eta j of the sum from k equals 0 to j of mass m sub k times the coordinate of body k, and eta j is the sum from k equals 0 to j of the masses. C sub j represents the center of mass of all of the bodies with index below j. So C of n minus 1, being the last of these, represents the center of mass of all of the bodies in your system. The subsequent coordinates in our modified coordinate set r prime are going to be the positions of each subsequent body. So Ri is the position of body I with respect to the center of mass of all of the bodies with lower indices. Again, as a practical example, think about the solar system. Your first coordinate for the solar system is the global barycenter of the solar system. And then your next coordinate will be the position of the first body. That would be Mercury. Remember, the sun in the original coordinate set is at index 0 with respect to the barycenter of the preceding bodies, which is just the sun. So r prime 1 in this case is the position of Mercury with respect to the sun. R prime 2 will be the position of Venus with respect to the barycenter of the sun and Mercury. R prime 3 will be the position of Earth with respect to the barycenter of the sun and Mercury and Venus, and so on and so forth. These are known as the Jacobi coordinates. The utility of this coordinate set is that the conjugate momenta, which we'll call p prime sub I of this modified coordinate set r prime sub I, is just m prime I times the time derivative of r prime I. And m prime I is defined as this eta value, eta of I minus 1, divided by eta I times m sub I, with the very first of these, m prime naught, being defined as eta of n minus 1, which is the total mass of the whole n-body system. So this is notationally cool in this ultra minimalist sort of way, but really the reason for going through the rigmarole of defining this rather complicated coordinate set is that it leaves the kinetic energy as a sum of squares of the momenta only. The total kinetic energy of our system, which was given in the original coordinate set as the sum from I equals 0 to n minus 1 of each of the body's momentum dotted into itself divided by twice their masses, now has exactly the same form in the p prime I momenta and the m prime I mass terms. The Hamiltonian is therefore now the Hamiltonian of the center of mass, so p naught prime dotted into itself divided by 2 m naught prime. We're calling that m naught prime is the total mass of all n bodies, plus a sum of n minus 1 Keplerian Hamiltonians. So this describes each of the two body orbits around the central body. Thinking about our solar system analogy, this is each individual two body orbit of each of the planets, all summed together. And finally, the Hamiltonian of the interaction, which takes this form. This is what we have gained here. This term is fully decoupled and ignorable. It has no effect on our dynamics, and we can cease to consider it. This is a collection of Keplerian two-body orbits, and we have gotten exceedingly good at propagating these very efficiently forward in time. This is fully analytically solvable and therefore can be considered a solved problem. We don't need to worry about it anymore. And finally, the hard part is now all concentrated in this interaction term. And for stable systems like the solar system, this interaction represents a small perturbation, and we can take advantage of that. One of the things that was very frequently done in the early days of computing these types of schemes was to expand this interaction term to first order in the ratio of mi to m0. This is really not necessary with modern computers. And so we're not really going to even consider it. It was a stopgap measure to allow for the computation on very limited hardware. And we no longer have that limitation. Instead, we are going to focus on the clever ways that we can mix our existing tools for efficiently solving this propagation and what we can do in terms of incorporating this interaction perturbation. And we start by returning to our second order symplectic integration scheme, which you will recall was defined for a case where the Hamiltonian was separable into two pieces and consisted of a symplectic map of the first piece of the Hamiltonian over half a time step times the symplectic map of the other piece of the Hamiltonian for a full time step, and then another half step closing out the first part of the Hamiltonian. In that case, we had split the Hamiltonian as a kinetic term and a potential term. But in this case, we can do exactly the same thing with our Kepler term and our interaction term. And as before, we can fully ignore the center of mass because it has no effect on anything else. So the basic algorithm is you drift all of the bodies on their Keplerian orbits for delta t over 2. You don't have to worry at all about symplectic mappings or anything else. It's you have an analytical solution for this, and so we can propagate these things exactly without any worry of losing phase or energy information. You then kick each body's momentum. So you change the momentum only without changing the coordinates according to the interaction term for the full time step. And then you proceed to drift all the bodies in their Keplerian orbits with their modified momenta for another delta t over 2. You can equivalently reverse this ordering and do half kicks and full drifts in the middle. The result is the same. You have a second order symplectic map. This is known as mixed variable symplectic integration and was first introduced in this 1991 paper by Wisdom and Holman. The main difficulty with this method is that as soon as either of the terms in the interaction Hamiltonian, as soon as either one of these two summations starts to get large, the method will start to fail unless your delta t is very small. And this will happen whenever any pair of bodies approaches one another closely, whenever any body gets too close to the central body or any body gets too close to any other body. If you're integrating something like the solar system, that's not a problem. Major bodies in the solar system don't get close to one another. It becomes a problem when you're introducing other masses like minor bodies, asteroids, dust, or spacecraft, which can very well come close to a planet. In that case, you're going to be forced to either use a very, very small delta t or to change your delta t, but we've already discussed the issue with changing delta t as you go along. That changes the overall Hamiltonian and means that you are no longer integrating the same system that you started with. Ignoring that difficulty for a second, the benefits of this method are that as long as the interaction Hamiltonian's magnitude is much smaller than the Keplerian interaction magnitude, you can increase the time step over something like a leapfrog scheme by a factor of the square root of the ratio of the central body to any other body. So m0 over m1 to the 1/2 power, and get reasonable results with a time step that is equal to approximately 1/20th of the shortest orbital period. And that's huge. That means that you can effectively take 20 time steps per orbit for the shortest orbital period and still preserve the symplectic structure and much of the total energy of the full system. So this represents a huge step forward in our ability to efficiently propagate n-body Hamiltonian systems, but it has severe limitations. It does not allow for close approaches, significant interaction between any pairs of bodies, and it also locks you into the timescale of the body on the shortest orbit. And so again, if we're integrating the solar system and we wish to include Mercury, then we are kind of limited in this scheme by the period of Mercury's orbit, which is very, very, very small compared to the period of the orbits of the outer planets. This is one of the many reasons why when this method was first applied to long-term integrations of the solar system, they really focused on just integrating the outer planets. The inner planets don't have a lot of mass, so they really don't affect things very much. And if you're interested in looking at the long-term stability over millions and hundreds of millions and billions of years of the solar system, it's okay for an initial cut to just look at the outer planets, Jupiter through Neptune.